Okay, let's start today's session. I'm going to start probability. Probability, simple one. So this is question number 9 and 17 part A. Question number 9 and 17 part A, applied paper. Very simple question. So consider there can be some experiments. There can be some experiments. Final outcome can be predicted. Some experiments, final outcome can be predicted. Some cases, final outcomes cannot be predicted. So as an example, consider tossing a coin. Tossing a coin, final outcome is not predicted, no? But we can say all possible outcomes, head or tail. Tossing a die, final exact outcome we can't predict, no? But all possible outcomes, no. This is known. 1, 2, 3, 4, 5, 6. Then all possible outcomes known, but final outcome, exact outcome, we don't know. Then in such experiment, to analyze those type of experiment, we use probability. So we use probability to analyze those type of experiments. Okay. Then tossing a coin, that experiment we call random experiment. Random experiment means that experiment we can repeat again and again with same condition, under same condition, and final outcome we don't know exactly. Then that experiment we call random experiment. Okay. Then we consider about random experiment and we consider about mathematical definition to analyze those type of outcomes. We do that thing using probability. Okay. Now anyway, this probability always happen with sets. Okay. You consider here a set, capital A set. Here this is we call null set. Here B 1. Here singleton set. Here consider C 1 2. Here consider set C D 1 2 3. Okay. Here same thing we can denote by, here this say we call null set. Here singleton set. Here n null, here n represent number of elements. Here number of elements 0. Here Na, here number of elements 1. Here consider NB, NC, here NB, NC, here number of elements 2. Here ND, number of elements 3. Okay. So here number of elements 0, we call null set. Here number of element 1, we say singleton set. Here number of element 2, number of elements 3, it goes so on. Here when you consider here this set, we can further we can break into subsets, no? Further we can break into subsets. So consider here all subsets, here null set 1, here 2, 1 and 2. Here these are possible subsets. Here this is the given set, then we can split into subset null 1, 2, 1 and 2. Here we call universal set. All possible subset. Here number of element 2, no? Here number of element 2 to the power 2. We denote by curl A. 2 to the power 2, 4. Here 1, 2, 3, 4. Here this case element 1, 2, 3. Then there will be number of subset 2 to the power 3. Here 2 to the power 2. Here number of element 2. Here this will be 2 to the power 2. And here number of element 3. Then here possible subsets n curl A. For this case, let's try to break it. Here null 1, 2, 3, and 1 2 1 3 2 3 1 2 3. Now count 1 2 3 4 5 6 7 8. Then n curl A equal 2 to the power 3. 2 to the power 3. That is 8. Now we have 8 element. Okay, now you consider curl A. This is curl A, all possible subsets. Then NA equal 2 to the power NA. 2 to the power NA. Okay. Then set mean collection of objects. Set mean collection of object. That can be numerical value, that can be any object. So anyway, set mean object, collection of object. Then here this one we call element of C. Here we call 2 is element of C. We can denote that one, 2 is element of C. And here 1 element of D, no? Here 1 element of D. Likewise, we can denote 2 is an element of C. Here 1 is an element of D. Likewise, we can further represent. And when you consider here this one as a set A, let's say set E, here set E subset of D, no? Then set E subset of D. Likewise, we can further denote E is a subset of D. Likewise, we can denote these sets. Okay. Then identify, we use probability, that is mathematical definition. Probability means mathematical definition. To analyze random experiment final outcomes, you consider probability. Random experiment means some experiment which can repeat again and again, but final outcome we don't know exactly. As an example, tossing a coin, tossing a die, we don't know final outcome, final exact outcome, but we know all possible outcomes. Okay. Now take your tutorial. First read that definition. Probability theory is the branch of mathematics concerned with analyzing random phenomena and qualifying uncertainty. It used to many fields, model reasoning about outcomes that are not deterministic. Okay, then final outcomes are not determined. Final outcome we don't know exactly. Then we consider probability to get mathematical definition. Okay, then set theory. Set is a fundamental branch of mathematics that deals with collection of objects. So this probability mainly connect with sets. Okay, that connect with set. Okay, it provides us mathematical including probability, logic, number theory, and more. Okay, that means set most commonly connect with probability. A set is well-defined collection of distinct objects. We denote by capital A, B, C, D. Likewise, you know everything. Then I go so soon. Then notations within curly bracket, we write that no. Here we write number set within curly bracket, comma separated one. Okay, comma separated one. Okay, then so element of a set, if X is in set A, we write simple X element of A. If X is not in A, we write X not element of A. So when you go to here, you consider, let's go to here. Here 4 not an element of D. Here we denote this way. 4 not an element of D, no? 4 is not an element of D. Not an element of D. Okay. Then here, when you consider this set, here countable, no? Finite set. This is finite set. But there can be infinite sets. There can be infinite set. You consider this example, tossing a coin. Okay, you consider tossing a coin. Then let's take this. Usually all possible outcomes we say sample space. Sample space. Then head or tail. Head or tail. Then tossing a coin until getting head. Getting head. Therefore now say sample space here first time head, first tail, second head, first tail, second tail, third head, tail, 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 head. We don't know end. We don't know end. No? Then here this is not countable. Number of element not countable. This is infinite set. This is finite set. Here finite set, infinite set. Then if the number of element countable, that is finite set. If the number of elements uncountable, then that is we call infinite set. Okay. Then null set contain no element. Here this is null set that not contain any element. And further, universal set contain all elements under consideration. All elements under consideration. Usually we denote by U. Okay. Now let's move a little further. Before that, you better to write these examples. Okay. So by the side there are small spaces now. You write these examples. Again go to this. Write this is null set. Here singleton set. Here NC to number of elements in C. Then NA represent number of elements in set A. Set A. Okay, just write one by one. First you write by the side, write down these examples with notations. With notation. Okay. Okay. Now better write these notations as well. Here 2 is C mean 2 is an element of C. 1 is D mean 1 is an element of D. 4 not element of D. 4 is not an element of D. Okay. Now you do with me. Do with me. Here A 1 2 NA equal 1 NA equal 2. Do with me. Here these are few examples. You better write that in another paper. NA equal 2. Then here this is curl A. You try to split all subset. Get all subset. Here null set 1, 2, 1 and 2. Then here in curl A, here this is we call curl A, 2 to the power NA, 2 to the power 2. We have 4 elements. By the side, write down this. Then A, 1, 2, 3. NA equal 3. Write with me. NA equal 3. N curl A equal, just curl A equal null set 1, 2, 3, 1, 2, 2, 3, 1, 3, 1, 2, 3. Write with me. Then for this case, n curl A equal 2 to the power NA, 2 to the power 3, 8. 2 to the power 3 equal 8. Here probability very simple question. Curl A, all possible subset. Set of all possible subset. Curl A is a set of all possible subsets. Curl A is a set of all possible subset. Okay, write it. Curl A, all possible subset. Okay, now let's move a little further. Okay, now here let's move to set operation. Here set operation, you consider here this is sample space. Here this is set A, here set B, here A intersection B, no? Intersection. We call A and B. Here A, here B, here this is called A or B, A union B, A or B, A union B. Here this is A, this is called complementary set, A dash, A dash. A dash means S minus A, S minus A. That is complementary set. So I have given that in page number 3, union, intersection, difference, complement. Okay. Then you consider here set A, here set B. Here this part we call only A or A minus B. A minus B, set difference. Here set A, here your intersection, no? Then only A we call set difference. Set difference. Here only A. Then when you consider this part, here A, B, this is called B minus A. B minus A. Only B. Only B. Okay, write with me. Only B. Here this is only A, here this is only B. Then there's small space there, no? Better write. Huh? Then when you consider here this Venn diagram, here A and here B, this is only A, only B. Then only one, we can say only one. Only one. A minus B or B minus A. That is we call only one. A minus B or B minus A. Okay, write them. This is equal only A. A dash mean not included A. Okay, that is not included A. Here A minus B mean only A. B minus A mean only B. Write them. Here A minus B, further you can write A intersection B dash. Here A and here A intersection B dash. Include A, not include to B. Okay, you have to remove all common elements. Consider set A 1, 2, 3, 4, 5, 6. Set B 2, 5, 7, 8. Then A minus B mean you take all A and remove common B value. Remove 2, remove 5, then 1, 3, 4, 1, 3, 4, 6. Then B minus A mean that include B all values but remove common values. Then 7, 8. B minus A 7 and 8, A minus B 1, 3, 4, 6. That include A element and not include common B values. Okay, that is set difference. We call set difference. Set difference. Okay, now further you see we have the Morgan's law. The Morgan's law, it says this: A dash intersection B dash equal A union B whole in dash. Here A dash intersection B dash, that represent A union B whole in dash. Here intersection goes to union. A dash union B dash equal A intersection B whole in dash. Whole in dash. This is called the Morgan's law. The Morgan's law. Now let's see. Here first one. Here A and B. Take here A. Take here B. A dash mean value without A. B dash mean value without B. Then intersecting region mean your common values. Here we have common values here. Therefore, we can see A union B, no? A union B dash also same. Here A union B, here full part, it dash mean excluded. Therefore, A intersection B dash equal A union B dash. A union B dash. Similarly, the other case, let's sketch Venn diagram. Here for this case, A dash, here A, here B. B dash, then union mean all shaded region, then intersection not belongs there, no? Then A intersection B dash. A intersection B dash. Here see A dash union B dash, A intersection B, here A intersection B is dash. Okay, then that is called the Morgan's law. The Morgan's law. So in that side, you better to represent that on Venn diagram. Go for that. Okay, then here all these are we call set theorems. Set theorems. Then probability directly deal with sets. Direct deal with sets. Then commonly you need to remember these operations, set operations. A dash mean not include A, complementary event of A, no? Then A intersection B, common value of A and B. A union B mean all values of A and B. Then A minus B mean set difference, include A, exclude B values. A minus B include A value but exclude B values. No? Set difference. Okay, now I told you there are few experiments type. Okay, few experiment type. So one type, final outcome directly unpredictable. It is not predictable. As an example, tossing a coin, final outcome we can't say, but all possible outcome we can say. Tossing a coin we can repeat again and again. We can repeat again and again. That experiment we can repeat again and again with same condition, but final outcome we can't exactly say, but all possible outcomes we can say. Then that type experiment we call random experiment. Tossing a die, then random experiment. Okay, then go to page number 4. That is the definition of random experiment. So somewhere by the side write down just examples. They are given, no? Examples for random experiments given. No? So given that tossing a coin head or tail, rolling a die 1, 2, 3, 4, 5, 6, drawing a card from a deck. So we have 52 combinations. Choosing a student at random. So there are many students. So then all possible outcomes there. Okay, that is random experiment. So with that random experiment, we have special technical terms. So one term we call outcome. Outcome, a single possible result. Single possible result. Tossing a coin, then one outcome tail, one outcome head, no? Then sample space. Sample space means all possible outcomes. Usually we denote by S, or otherwise we denote by ohm. You better write this notation as L. So I have given sample space there. You better write down this notation as L. Ohm. Then set of all possible outcomes, that is sample space. Event, any subset of a sample space. Event means any subset of sample space called an event. Okay, so somewhere there just write down sample space can be a finite sample space. Sample space can be a finite sample space or an infinite sample space. Sample space can be finite sample space or an infinite sample space. Write another example. Tossing a coin until getting head. Until getting head. Until getting head. You write sample space. Sometimes first outcome can be head. Tail, head also another outcome. Then tail, head another outcome. Tail, head another outcome. So on it goes. Then infinite sample space. Okay, write that example. Sample space can be finite or infinite. As according to the experiment, we can identify whether it is finite or infinite. Okay. So here this experiment, tossing a coin until getting head. Then first attempt we can get head, or first tail then head. Second attempt we can get head, then tail, tail, head, tail, 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 head. It goes so on, infinite sample space. No? First, just identify these technical terms. Now, take this example. Here, sample space, head or tail. Toss in a coin. Then, subset of this we call events. All events, possible events, null. Then all subset, head, tail, head or tail. Then here this is we call event space. Event space. Okay, that would look again like curl, event space. Then here these are events. Events. Event is a subset, a sample space. Better write that one as well. Here this is random experiment, toss in a coin. Then here this is event space. Then all possible subsets, that is event space. Then these are we call events. So this event we call get in head. Here get in tail. Get in head or tail. Here get in nothing. Okay. These are event space. Then event is a subset of a sample space. Subset of sample space. Okay, just write that one as well. Okay, now let's go to probability definitions. So in probability, we have three definitions. So one is historical definition. Again, we call that is classical definition. Okay? That is very simple definition. So here it is. You consider an example, toss in a coin. We get sample space, head or tail. Here get in head, one event, no? Here this is sample space. Then when you consider ns, that is h, that is 2, no? Then take event e, get in head. Then event e, we have h only. Then ne equal 1, no? Ne equal 1. Then first definition, probability of getting h, head. Probability of getting head, we denote by this notation, ph. So here, nh, yeah, let's say e, event, let's say h, event h, getting head. Here we denote by nh divided by ns. This is our classical definition. Here nh mean 1, ns mean 2. Then get in head probability half. Consider sample space 1, 2, 3, 4, 5, 6. Here roll in a die. You consider event A, consider 1, 2, value less than 2. Here this event, value less than 3. Then if you need to find PA, probability of A, we denote by NA divided by NS. This is first definition. Then NA mean 2, NS mean 6, then 1/3. Then P even, N even divide by NS, 1, 2, 3. 3 divided by 6, 1/2. That is classical definition. Okay. So go to page number 5, identify that. Write that example. That is classical definition of probability. Yeah? Very simple definition. You consider number of element in sample space and number of element in that event. Then the division we call probability. But this is not always applicable if sample space, infinite sample space, then this is not possible. No? If it is infinite sample space, it is not possible. Then this definition we can get, it is limited. Here we can use for limited cases. Okay, write examples. Okay, now go to page number 10, question set 1, simple probability, question set 1. Okay, complete soon. You just write answer, I'll give you 2 minutes. Just write answer, question, page number 10, first 10 questions. Question set 1, page number 10, first 10 question. That's with classical definition. Do soon. A coin tossed once, what the probability of getting head? 1/2. A die is rolled, what is the probability of getting a number less than 5? Here 1, 2, 3, 4, 5, 6. Less than 5, here this is the set. 4 divided by 6, 2/3. Third, a card is drawn from a standard deck of 52 cards. What is a probability of getting head? So we have 4 kings. 4 divided by 52. Here 1 divided by 13. 4. 2 coins are tossed together. What is the probability of getting 2 tails? Then here head, tail, head, tail. So sample space we have 4. What is the probability of getting 2 tails? 2 tails. Here there's 1, 1/4. Consider sample space. Then the required case, you write classical definition. 5. A number is chosen at random 1 to 10. What is the probability number is even? A number is chosen random from 1 to 10. Consider included 1 and 10. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then here total count 10. Even 1, 2, 3, 4, 5. 5 divided by 10, half. Complete. Six, a jar contains 3 red balls, 2 green balls, 5 blue balls. But the probability of drawing a green ball. Then altogether we have 10 balls. Say P, we need to consider green ball. Let's say PG. Then altogether we have 10 and green balls 2. Then 1/5. 7, a letter contains chosen at random for word probability. PRO BA, BI, LITY. What the probability of choosing a vowel? Here we have all count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Then vowels A, I, O. Then we have 1, 2, 3, 4 vowels. 4 over 11, no? Question number 8. A dice rolled twice. What is the probability of getting 6 on first roll and even number in second? Write sample space 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So here a die rolled twice. What's the probability of getting 6 on first roll? Yes, 6 on first roll. So that is exactly given. Now here the possibility here 2, 3, 4, 5, 6. So here we have 6 count. So even number on the second, even number. Here 1, 2, 3. 3 of 6. Don't consider 36. Huh? So here first roll exactly 6. First roll exactly 6. Then second roll we have 6 possibility. Then by that we have even possibility 3. 3 divided by 6. Nine. A bag contains 4 white balls, 6 black balls. One ball is drawn. Then white ball 4 divided by 10. 2 divided by 5. 10. What the probability of getting odd number when single dice rolled? Odd number. Then 3 divided by 6. 1 over 2. Very simple. Then classical definition, very simple. Classical definition not always possible, but it is very simple. This example, come to this example, okay? Now consider, here you consider, you go to new page. Here, white ball 6, black ball 4. Okay? Here, select 1. Select one ball. Then P white 6 over 10. P black, do with me, 4 over 10. Select one ball. Then you select 2 balls at once. Now I'm going to select 2 balls at once. So selecting 2 balls, we can consider take one and put one side, take another one and put the other side. So getting 2 at once again look like take one and place it one side and take another one. Okay. Then here we can sketch tree diagram. First ball. Here white or red, white or red, white or blue. Then here total count 10, 6 over 10. Now here black 4 over 10. Now second ball, again white or black, white or black, white or black. Now we have take one outside, no? Then remaining 9 further we have. Now I have already taken white ball. Then white ball now 5. 5 divided by 9. Now black balls remain 4. Now black ball is taken. Now black ball 3. White ball 6. Then black ball is taken. Now black ball 3 over 9. Okay. So here select only 1. Here select 2. Then if you need to find probability of getting 2 white balls, here you can denote this way. P getting 2 white balls. Then here it is 6 over 10 times 5 over 9. P getting 2 black. Here it is 4 over 10 times 3 over 9. So when you go along this path, we have to multiply. When you consider 2, we have to add sum rule and product rule like permutations and combination. Okay, do with me. Do with me. P, 2 different color. So here white, black, black, white. 6 over 10, 4 over 9, 4 over 10, 6 over 9. 6 over 9. Okay. Just do alone. Here first one taking 1 ball, second one taking 2 balls at once. Here selecting 2 balls at once. Okay. Now similarly you try to select 3 balls. Select 3 balls. At once. Then white ball 6, black ball 4. You get tree diagram first. We have combination technique, but I am telling here to get tree diagram. White, black first ball, second ball white, black, here white, black, third ball white, black, white, black, white, black, white, black. Here first ball, second ball, third ball. Now here 6 over 10, 4 over 10, here 5 over 9, 4 over 9, here 4 over 8, 4 over 9, 4 over 8, here 5 over 8, 3 over 8, here 6 over 9, 3 over 9, 5 over 8, black, white, black, 3 over 8, here 2 black, 6 over 8, 2 over 8. 2 over 8. So one by one you have to think. One by one you have to think. Then here, probability of getting 3 white balls. 3 white balls. Here go with this path. 6 over 10, 5 over 9, 4 over 8. P, 3 black. Go along this path. 4 over 10, 3 over 9, 2 over 8. White, black, white. Here white, black, white. 6 over 10, 4 over 9, 5 over 8. Likewise, you can select one. Then when you go along this path, you can multiply. Here P, 2 white, 1 black. 2 white, 1 black. Then white, white, black, white, black, white, black, white, white. That's it, no? Then 2 white, 6 over 10, 5 over 9, 4 over 8. White, white, black. White, black, white. 6 over 10, 4 over 9, 8 over 5 over 8. Plus black, white, white. 4 over 10, 6 over 9, 5 over 8. No any other combinations. So by the tree diagram, we consider sample space kind of thing, no? Then all possible outcomes. Then 2 white, 1 black. Okay. Now you go to here this example. Here this contain 3 white balls, 2 black balls. Here this contain 4 white ball, 4 black balls. So first I'm select one and put that one here. Then randomly I'm going to pick one. First I select one and put into this bag. Here first bag, here second bag. Then first bag I select one and put into second bag. Thereafter randomly select another one by second. So here the tree diagram now. Here first bag, white or black. So white possibility 3, black possibility 2. 2 over 5. So now go to second bag selection. That also white or black. White or black. Now I have taken white ball. When I put white ball here, all together here 8, now 9. So 5 white balls now. So here 9, I have taken white ball now, then only 4 black balls. Here black ball is taken, put it here. Then all together 5 black balls. Then 4 white balls. So black ball is selected. Now we have 5 black balls. So when you consider last one, so final last P white ball selection. White ball selection of second bag. Now you have to consider here one, we have 2 cases. Take this and take this. Then 3 over 5, 5 over 9 plus 2 over 5, 4 over 9. Continue. Here white ball 2 cases, 3 over 5 times 5 over 9, 2 over 5 times 4 over 9, then add them. That is selecting one white ball, bag 2. Then P, here P represent probability of one white ball selection of second bag white ball selection. Then probability P, black ball selection of second bag. Here these two, no? 3 over 5, 4 over 9, 2 over 5, 4 over 9. Five over 9. 5 over 9. Okay. Now come to this example. Here card pack. So we have 52. So 26 red, 26 black. So here red, black. Then again we have 4 sections. We have 4 cases now. Diamond, heart, okay. Then select, I'm going to select one. Here P, get in one black card. So we have 26 black card, altogether 52. So P get in a king. Get in a king. Okay, do after that. Altogether 52 cards, half red, half black. So 13, 13, 2 sets, diamond and hearts. And here 2 black cards. Then here all 13 are different. 4 kings, so on, 4 ace, then 4 10 values, 8, 4, so on. Here A, 2, 3, 4, 5, 6, 7, 8, 9, 10, J, Q, K. Okay, here 4 kings. Now P, get in a king. So here we have 4 kings, altogether 52. We have 4 kings, altogether 52. Okay. P, get in a red king. So we have 2 red kings, altogether 52. All kings 4 divided by 52. Getting a red king, we have 2, 2 divided by 52. P, red card or a king. Red card or a king. Then altogether we have 52. We have 26 red card. So inside that we have 2 kings. Then outside we have another 2 kings. 2. 28 divided by 52, no? 28 divided by 52. Red card or a king. 26 red card. 4 kings. 2 red kings, no? Then that including 26. Then remaining 2 black kings we have to include. Then 26 red and 2 black cards, black kings. Then altogether 28 divided by 52. 52. Now see this one. This is classical definition, okay? Classical definition of probability. That is very simple definition. But this is not always possible. This is not always possible. Go to page number 5 now. Page number 5, limitation of historical definition. Limitation of classical definition. Only works for all outcomes are equally likely. That is very important. Underline that one. Equally likely. Equally likely. So by this side write down, equally likely means, just write down there. Equally likely mean the possibility of occurrence of each outcome. Equally likely mean the possibility of occurrence of each outcomes. Each outcome are same. Are same. Then consider a coin. So we have possibility getting head or tail, half, no? Then equally likely fair coin or unbiased coin. Unbiased coin, half. So if it is biased, we can't get that classical definition. If it is biased, we can't get classical definition. We have to think another one, another definition. Okay, then if it is equally likely, then classical definition possible. Otherwise, it is not possible. Then again, for infinite sample spaces, classical definition impossible. Infinite sample space. Sometimes we get infinite divided by infinity. So consider sample space. N is now infinite, no? Infinite sample space. You consider event that also, if that also infinite, then PA, we say NA divided by NS, no? Then NA infinity, NS infinity, it is undefined, no? Then infinite sample spaces, this classical definition won't work. That won't work. So again, for these type of things, especially biased thing, not fair, unfair things, we have frequency definition. We have frequency definition. You consider that you have a coin that is biased one. So we do this, say, we toss a coin 10 times. We toss a coin 10 times. So we toss a coin 10 times. So get in head. So you see, you think we get 6 times. Then relative frequency of get in head we call 6 divided by 10. This is we call relative frequency. So previous case we did that event at once, no? At once. Now here we have to do same experiment several times. So here this is equal relative frequency. Relative frequency. Then we denote by n divided by capital N. This is relative frequency now. Okay. Then when n goes to infinity, that means limit capital N goes to infinity, simple n divided by capital N. Here further onwards we say this is PA. Here consider A relative frequency. Say here A relative frequency of getting, let's say H. Let's say getting H. Then we say this is pH. This is pH now. Okay. In series, we know convergence, we know convergence. When n goes to infinity, some cases, the sum of sum, it tendency towards finite value. Then that is equal convergence. So here this case, when we doing an experiment 10 times, when we toss a coin 10 times, we get 6 times head. So this is equal relative frequency. Then this accuracy we can build, the number of experiment with the number of experiment. So here if we done that into 100 times, then we can count head now 66 times. Then this is relative frequency. So if we did that 1000 times, 669, then here it is. Then 10,000 times, 6,576, so on. So when this occurrence, when we do this experiment infinite number of times, then this fraction come to finite value. That is we call frequency definition. But this frequency definition we won't consider because it is practical one. Then no need to worry about that definition. But anyway, we have frequency definition. This frequency definition works for biased things. Okay. Now read that frequency definition, page number 5. The frequency definition of probability defines it based on the long run relative frequency of an event occurring repeated trials of an experiment. So we do that experiment repeated times. So it is long run relative frequency. Formal definition, the probability of event A is the limit of the relative frequency as the number of trials approach infinitely, PA, limit n goes to infinity, n over n. Simple n is the number of times event A occurs in n trials. So we did that experiment for n trials. Then event A occurs simple n times. Then simple n divided by capital M we call relative frequency. So if that n goes to infinity, that fraction tends to finite value. Then that finite value called frequency definition. Okay, don't worry about that one. So that also not always possible. There can be some experiments, non-repeatable experiments, then that is not work for that. Here another thing, we need to do large number of trials. Then to get high accuracy, we need to do large number of times. Then that is somewhat difficult. Okay. Then thereafter we need to go to axiomatic definition. That is very important one. So under probability, I told you probability mean we do some experiments. So especially random experiment. So in that random experiment, we say that experiment we can repeat again and again, but final outcome exactly unknown, but all possible outcomes are known. Then to analyze that type of random experiment, we use probability. Okay. Then all possible outcomes we call sample space. So when we get a subset of that, we call that is an event. Then classical definition or historical definition So NA mean, sorry, PA mean NA divided by NS, no? NA divided by NS. That is classical definition. That not always possible. So then we have to go to frequency definition. For bias, unfair things, we have to go to frequency definition. Then we have to repeat same experiment, few trials, no? We have to do 100 times, 1000 times, so on. Then if the occurrence of A simple n, the total trial capital N, then simple n divided by capital N we call relative frequency of A. So if that limit capital N goes to infinity, then that fraction tends to finite value. That finite value we call probability of occurrence of A. That is frequency definition. That is not always applicable for us. Then thereafter we have to go to another mathematical definition, that is called axiomic definition. Then we deal with 3 axioms to develop this probability. Okay, we discuss 3 axioms to develop this probability. Okay, that is axiomic definition. So that is modern approach. That is the modern approach. That is mathematical approach. Okay. Then that is rigorous approach. That is the actual definition. That means clear, exact definition of probability. That is high mathematical definition. Axiomic probability. So we have to think this way. So let S be a sample space. That means all possible outcomes. Let capital A be an event. Capital A be an event. That means that is subset of A. Subset of A. A probability function P, we call probability function. Okay. Usually we write function fx now. Here we call function of x. Then here we call probability function. We usually denote by P dot. This is P dot mean probability function. Okay. When you replace this dot by PA, you replace dot by A, we call probability of occurrence of A. We say probability of occurrence of A. So without P we say occurrence of A. Then when we put P, we say probability of occurrence of A. Then A dash not occurrence of A. Then if you put P, we say probability of not occurrence of A. Then A intersection B, we say occurrence of A and B. When we put P, we say probability of occurrence of A and B. No? Probability of occurrence of A and B. Then here this function we call probability function. We call probability function. Okay. So that probability function, their special thing, first axiom, non-negativity. That means that you have to think the probability is always positive. That is non-negativity. First axiom, probability is positive greater than or equal 0. Non-negativity greater than or equal 0. Then second axiom, normalization. So PS equal 1. PS equal 1. S means happen one thing, happen anything. The probability of entire sample space is 1. The probability of the entire sample space. That means if you toss a coin, something will happen. Okay, head or tail, something will happen. Then the probability is 1. When a tossing a coin getting 1, impossible, no? Then that probability is 0. When tossing a coin getting 1, impossible because we get head or tail. Okay, then 1 is not in our sample space. Then probability always in between 0 to 1. Probability always in between 0 to 1, included 1, included 0. Okay, included 1 and included 0. Then additivity, that is very important one. Okay, now let's go one by one. This is very important definition. Okay. Now here we have random experiment. Then we get sample space. So by that we can create event space. event space, we denote by curl A. So those events we can denote by A, B, C, so on. So this is probability function. Then PA, probability of getting A. So first axiom, PA greater than or equal 0, non-negativity. Second axiom, PS1. PS1. Then third axiom, you consider AB mutual exclusive one. I write it here. Third axiom. Take this one. Here we have mutual exclusive events. AB are mutually exclusive events. So mutual exclusive means disjoint. Here this is A, this is B. Then mutual exclusive means disjoint. That means A intersection B null. So such case, when you consider probability of A union B, we say PA plus PB. That is our definition. So A and B are mutually exclusive mean they are disjoint event. As an example, when you toss a coin, getting head and getting tail are mutually exclusive. No? That cannot happen at once. Those type of event we call mutually exclusive, disjoint. Then union of those type of probability of union of those type of event we can write as sum. Because these are disjoint event. So now for probability we have three axioms. So the modern definition, axiomic definitions comes with three axioms, that is definite. Okay, we can always applicable. PS1, probability always non-negative. For mutual exclusive events, union we can write as the sum. That is axiomic definition. Okay, so you go to that axiomic definition part. So here you better write these things. So mutual exclusive events, there's mutual exclusive event. No? You better to sketch the Venn diagram. Better to sketch this Venn diagram. Mutual exclusive mean disjoint, A intersection B null. That is given, no? A intersection B null, but you better to sketch this diagram. Then PA union B, PA plus PB. Just sketch diagram. There is just sketch diagram. That is axiomic definition. Okay, here you have to identify random experiment, sample space, all possible outcomes. So when we combine events, when we combine elements, we can create events, no? Then all possible subset we call event space. So we can put all events to probability function. This is probability function we denote by P dot. Then we have to replace that event. We have to replace dot by that event, PA, PB, PC, so on. This is we call probability function. So you better write this one. This is probability function, P dot, probability function. Okay. Just get this idea first. Huh? So in probability we have three definitions. First, historical definition, very simple. That also usable, but not always. But for fair and unfair incident, we have to consider frequency definition. But that also again not possible always. Then the modern definition comes with axioms. We have 3 axioms. So based on that axioms, we develop that probability. Based on that axioms. So probability non-negative, probability greater than or equal 0. PS1. PS1. For mutually exclusive events, union we can write as sum of the probabilities. Those are 3 axioms. So based on that axioms, we have theorems on probability. Go to next page, page number 7. So the theorems are given. P null 0. Here P null 0. Based on that axiom, we can create first theorem P null 0. Second theorem P A dash 1 minus P A. Third theorem P A intersection B. P A equal P A intersection B plus P A intersection B dash. Fourth theorem P A union B. Here P A plus P B minus P A intersection B. P A intersection B. Don't mislead with this. Don't mislead with this. So previously I told you P A union B, P A plus P B. No? But that is only for mutual exclusive. So this is general case. A union B, usually P A plus P B, we have to remove intersection. This is for general one. This is for mutually exclusive one. These are the theorems. And we have fifth theorem. Consider A, B. Here A is subset of B. Then when you put probability PA, PB, so now that becomes to inequality. Then A means subset. No? Then here A inside B. Therefore that probability of getting B, probability of getting A very small, where A is small. No? Then here subset, then when we put probability, it appear like this. These are theorems on probabilities. Theorems on probabilities. Okay? First analyze. You can directly take these theorems as well, but these theorems are based on the axioms. No? These theorems are based on axioms, but these are always directly applicable. So similarly, so if you need to get P B dash, now you directly write 1 minus PB. 1 minus PB. PB dash means 1 minus PB. Okay. Now further, if you have P A intersection B dash, now you write 1 minus P A intersection B. So on you can write. Here P A intersection B plus P A intersection B dash. Then PB, you write P A intersection B plus P A dash intersection B, no? P A dash intersection B. Clearly get the idea. This is general one, okay? This is P A intersection B, A intersection B dash. Then if you need to get B here, PB, A intersection B, A, P, A dash intersection B, no? Then dash will change. Then here PA, A intersection B, A intersection B dash. Then PB, A intersection B, A dash intersection B. So on we can further create many formulas. Okay? Okay, these are axioms. We have to prove them. Huh? Before that, let's use them. Now let's do 2-3 questions. Go to last page, page number 11. Question set 3. So that comes with those formulas. Okay, you start doing that. Okay, now check your answers. Question number 1, I'll do it soon. Sample spaces, disjoint events, PA union B equal PA plus PB. Point 3, point 4, point 5. Question number 2, if the sample space S contain 5 equally likely outcomes and event A contain 2 of those, what is PA? PA 2 of 5. 3, let A and B two mutually exclusive events, PA 0.6, PB 0.5. Determine if this is possible under axiomic definition. P A union B equal PA plus PB now. PA plus PB, PA 0.5, 0.6, 0.5, here 1.1. Here maximum value, PA union B maximum value 1, then this is impossible. Impossible. So that must be less than or equal 1, otherwise it is impossible, no? Then maximum 1 PS, no? PS 1. This is impossible. Then question number 4, PA 0.7, PA dash 1 minus PA, 1 minus 0.7, 0.3. 5, PA union B equal PA plus PB minus PA intersection B. Here fourth theorem. Then PA 0.4, 0.3 minus 0.2, 0.5. 6, A union B PA intersection B equal PA plus PB minus PA union B. Okay, PA 0.5, PB 0.4, 0.85, 0.05, 0.05. Okay, I'll give you further more questions. Okay, now you come to this question. If PA 308, PB half, PA intersection B 1/4, PA 308, PB half, PA intersection B 1/4. Find, okay, you do one by one. PA union B, PA dash, PB dash, PA union B dash, PA dash intersection B dash. Do alone, do soon. PB intersection A dash. You directly apply theorems. A union B, PA plus PB minus PA intersection B. These are part A question type, part A standard questions. You directly have to deal with these formulas. Then PA 308, 1/2, 1/4. Then 8, 3, 4, 7, minus 2, 5. 1 minus PA, 1 minus 3 over 8, 5 over 8. 1 minus PB, 1 minus 1 over 2, half. 1 minus PA union B, we got that before, 5 over 8, 3 over 8. Then use the Morgan, A union B whole thin dash. So we got that now, 3 over 8. Then here only B, we write here PB minus PA intersection B. Then only B here now. Then B half, intersection B 1/4, 1/4. Okay. Then second question, if PA union B 7 over 8, PA intersection B 1/4, PA dash 5 over 8, PA dash 5 over 8, find PA PB, PA intersection B dash. Continue. PA 1 minus PA dash 1 minus 5 over 8, 3 over 8. Here PB, here PA union B equal PA plus PB minus PA intersection B. Then by this you find PB. Then PB, subject this PA union B 7 over 8 minus PA 3 over 8. Then plus PA intersection B 1/4, no? PA 3 over 8, A union B 7 over 8. Okay, here 4 over 8, 3/4. Here PA minus PA intersection B, PA 3 over 8, 1 over 2, 1 over 8. Likewise, you deal with theorems. Okay, do this. Okay, here P intersection B, PA plus PB minus PA union B, PA 1/4, 1/3, half. Get common denominator 12. Here 3, here 4, here 6, 1. Here only A, PA minus PA intersection B, PA 1/4, A intersection B, we got that 1 over 12, then 3 minus 1, 3 minus 1, 2 over 12, 1 over 6. Here the Morgan PA union B whole thing dash 1 minus PA union B, 1 minus PA union B, here half. Here only B, PB minus PA intersection B, PB 1/3 intersection 1 over 12, then get common denominator 4 minus 1, 3 over 12, 1/4. 1/4, no? Okay, next. If PA 0.6, PB 0.4, PA union B 0.76, find PA intersection B, PA union B dash, PA intersection B dash, PA dash union B dash. Continue. Here PA 0.6. Okay, here PA plus PB minus PA union B, 0.6, 0.4, 0.76, here 0.24, 1 minus PA union B, 1 minus 0.76, 24. 1 minus PA intersection B, check simplification, 1 minus 0.24, 0.76. Then PA intersection B whole thing dash, 1 minus PA intersection B dash 0.24, 0.76. Check simplification. Okay. Now let's move further. Here check this one. Here these are events, okay? Here these are events. So here we say the occurrence of A, the not occurrence of A. Here the occurrence of A and B. Here the occurrence of A or B. Here the occurrence of only A. The occurrence of only A. Okay, you better write with me. Yeah? So here this represents the occurrence of A, the occurrence of the not occurrence of A, the occurrence of A and B. Here the occurrence of A or B, the occurrence of only A intersection B dash union A dash intersection B, the occurrence of only one. We say only one. Here A or B, only one. Only one, only A or only B addition. Here the occurrence of only one. Write that. These notations are very important. You have to remember this technical word. Just write some. If you put probability function here, PA means the probability of occurrence of A. The probability of not occurrence of A. Likewise, okay. Now here it only have event, no? We only have event. Then first on the occurrence of A, the not occurrence of A, the occurrence of A and B. Here the occurrence of A or B, the occurrence of only A, the occurrence of only one. The occurrence of only one. Okay, no need to write all, but just write one or two. The probability of occurrence of A, the probability of not occurrence of A. It goes on. The probability of, we write the word probability, no? Okay, just write 1, 2. Now we can go to theorem proofs. We can go to theorem proofs. So I told you the modern definition of probability, axiomic definition, no? So that based on three axioms. First one, probability positive, greater than or equal 0, PS1. For mutually exclusive event, PA union B equal PA plus PB. We have three axioms, no? Okay, now let's prove theorem number 1, P null equal 1 equal 0. Yes, first theorem. Okay, see this one first. So you consider S and pi. S mean all, pi mean null. So when you intercept, definitely that is null, no? S mean all, pi mean null. Then S and pi, no interception, no? No common values. Then if we have S intersection null equal null, therefore you can say S and pi are mutually exclusive, no? If intersection null, then events are mutually exclusive. Then if events are mutually exclusive, we can consider third axiom, no? Okay, now you consider S union pi. See what is that? S union pi, definitely S, no? Now probability function put here. Put probability function both sides. Then since S and pi are mutually exclusive, this union we can write as sum, no? Is it okay? If mutually exclusive events, then union we can write as sum. Third axiom. Then cancel PS, then we get P pi 0. That's how we prove. Then P null 0. That's how we prove. Okay. Then go to page number 7. There's small space. The theorem probability P pi 0. Okay. In that space you write that. Do that proof. So at the beginning you have to say S and pi are mutually exclusive, then only we can apply third axiom, no? That is theorem number 1 proof. Then theorem number 2 proof, PA dash equal 1 minus PA. PA dash equal 1 minus PA. See the proof here. Now you check A intersection A dash. So we know this is null, no? A and A dash won't intercept. That don't have common values. Therefore, you say A and A dash are mutually exclusive. Now check A union A dash. So we know that is S, no? A and A dash S. Now you put probability A union A dash PS. Then for mutually exclusive events, union, we write addition PS. So here third axiom, then PA plus PA dash PS equal 1. Here second axiom. PS equal 1, second axiom we can directly get. Here union we can write as sum, third axiom. Then finally PA dash equal 1 minus PA. That is second theorem proof. Second theorem proof. Within that space, just do that. So at the beginning you have to say A and A dash are mutually exclusive. Then only you can write sum, no? Then third theorem proof. Here the theorem PA equal PA intersection B dash, PA intersection B plus PA intersection B dash. Here let A intersection B intersection A intersection B dash. See what is this? So you see here Venn diagram. Here A, here B. A intersection B is this. A intersection B dash is this. Then they don't intercept, no? Then null. Therefore say A intersection B and A intersection B dash are mutually exclusive. So now think A intersection B union A intersection B dash. That is full A, no? A intersection B union A intersection B dash. Here A intersection B, here A intersection B dash. Their union create A. Then you put A. Now put probability A intersection B union A intersection B dash equal PA. Now since A intersection B are mutually exclusive, then you can write here sum. That is third theorem proof. Third theorem proof. Here these are mutually exclusive, then you can write union as sum. Third axiom. Third axiom. Then by axiom we can prove the theorem. Okay. Then next theorem, PA union B equal PA plus PB minus PA intersection B. We're going to prove that one. So here you can take Here this proof. PA intersection B plus PA intersection B dash here, okay? PA intersection B dash. That is PA, no? PA. Similarly, PA intersection B, PA dash intersection B, PB, no? Take previous theorem now. Check this now. Here PA equal PA intersection B plus PA intersection B dash. Similar PB equal PA intersection B plus PA dash intersection B. Second, add them. PA plus PB equal to PA intersection B. Here these two are same. PA dash intersection B, PA intersection B dash. Now take one intersection the other side, because then we can create right side. Then PA plus PB minus PA intersection B. PA intersection B, PA dash intersection B, PA intersection B dash. Now think what are they? Now think what are they? See, here A, here B. A intersection B is this. A dash intersection B mean only B. Here this. A intersection B dash mean only A. Here this. They are mutually exclusive, no? Those events are mutually exclusive. A intersection B, A dash intersection B, A intersection B dash are mutually exclusive. Then for mutually exclusive events, union we can write as sum, no? Then here's this sum write as union, converse. Here this sum write as union now. Then PA intersection B union A dash intersection B union A intersection B dash. Then see what is that result. Here union of these, that is A union B, no? PA union B. That's how we prove. Okay, do that proof. Now let's move a little further. So we consider about two events now. So two events inside sample space AB. Now if you have A union B union C, PA union B union C. See, now here we have three events A, B, C. First get A intersection, first get PA. Now at PB, at PC. Now remove this common part, PA intersection B, remove this common part, PB intersection C, and remove this common part, the other common part, PA intersection B. Now here mid common one we have completely removed, no? Now thereafter you add it, PA intersection B intersection C. So remember, this is another important formula. PA union B union C equal PA plus PB plus PB PC minus PA intersection B minus PB intersection C. Here A intersection C and add A intersection B intersection C. Here this is PA. Here see clearly. Here PA. Okay. Here PB. Now this part fully common. This is PC. So you add them all. Then here we have repeated 2 times A intersection B, A intersection C, B intersection C. Now remove that one. So if you remove that one, here this part A intersection B intersection C completely gone. No? Thereafter you have to add it again. So here this is another important formula. I haven't given that there. You better write this formula. Write as theorem. Write as theorem. Okay. Now we have to go a little further. Up to now we have discussed the probability. Probability means mathematical definition of uncertain events, uncertain result. Therefore, there are random experiments. So random experiment we can do again and again with same condition, but final outcome exactly unknown, but all possible outcomes are known. Then to define those outcomes, we use probability, that is mathematical definition. Okay. Then here this event, if you consider any experiment, we have result. No, those results are a set. Those results is a set. Okay, that all possible outcome we call sample space. So when we split that into some events means subset of that sample space, we call event. Then to consider the occurrence of that event, we use probability to measure it. We use probability to measure it. So first definition, classical definition or historical definition. Very simple definition, n divided by ns, na divided by ns. So thereafter we go to frequency definition, because there are some weaknesses in classical definition, not always possible. Then that case we have to go to frequency definition. So we have to do same practical infinite loop. No, we have to do same practical again and again. So simple n divided by capital N I introduce as relative frequency. As capital N goes to infinity, then n divided by m fraction goes to finite value. That is we call the probability now. That is frequency definition. Frequency definition. Thereafter axiomic definition. Then directly we mainly concern about modern definition that deals with 3 axioms. PA greater than or equal 0, PS1 for mutually exclusive event probability is the probability addition. That is 3 axioms. So based on that axioms, we got few theorems. P null 0, PA dash equal 1 minus PA, PA equal PA intersection B plus PA intersection B dash, and PA union B equal PA plus PB minus PA intersection B, so on. No? So on. So here another extension of that theorem, another extension is that PA union B union C equal PA plus PB minus plus PC minus PA intersection B minus PB intersection C minus PA intersection C plus PA intersection B intersection C. That is some extension. Okay. Now further we have discussed only about conditional probability, one small theorem. And second we have to discuss about partition of a sample space. With that one we have discussed total probability theorem and Bayes theorem. Okay, but we have capacity to do all questions without considering total probability and Bayes theorem. Without knowing that total probability and Bayes theorem, we can do question by using tree diagram. We can do, okay, but we have to analyze both. Now, just go to next topic. Conditional probability I have given there. Okay. Now here you consider there are two events, just like likelihood means they close together. Then here the definition PA given B, this says that probability of occurrence of A, B has already occurred. Here B has already occurred. Or probability of occurrence of A given B has occurred. Here down one has occurred. Already occurred. Then here the definition PA interception B divided by PB. Here this is our definition. Now you take this one as another theorem. Take that one as another theorem, okay? So here this notation says that the probability of occurrence of A, the B already has occurred now. B already has occurred. Okay? So you consider if A and B are independent, then PA given B, when they are independent, no worries, B already happened, but no worries, we can just forget B. Then this is already A, no? Think PA given B, here PA given B, we write PA interception B or PB, no? Okay. So as an example, you consider this tree diagram. Here say A, here say B. Here this is equal PA. This is equal A already occurred. We think about B. That is conditional probability. We already discussed that. So here PA. So thereafter next A already occurred. Now we think about B. Then here PA. Here we say PB given A. PB given A. A already occurred. Okay. Now if you see that one, you directly write this definition PA given B equal PA interception B or PB. B denominator, numerator, interception. So this is very important. If A and B are independent means that not depend each other. So when they don't depend each other, then we can forget this A about A, no? Then the probability of A given B, you can directly write PA. Don't worry about the happening of B, no? We can forget that one. So anyway, this one, PA interception B over PB, now PA. Now cross multiply, PA interception B equal PA times PB. Now you think this is always possible formula. That is always possible formula. But here this one, not directly possible one. Okay. Okay, this is not directly possible one. This can apply only for independent events. Okay. Okay. Just read that one. Page number 7. Page number 7. Page number 7. Just read. The conditional probability measures the likelihood of an event given that another event has already occurred. So one event already occurred, we discuss about another event. So the definition, let A and B are two events, assume that PB greater than 0. Then PB greater than 0 means it has already occurred, no? Then the conditional probability of A given B is PA given B equal PA interception B or PB. Here the definition that is given. It says that the probability that A happened given that B already happened. Then downstairs one already happened. No? Then important notes, PA given B not equal PB given A. So it is different, no? If A and B are independent event, then PA interception, here this is PA, no? Okay, under that you better write the other two. So page number 7, last part, you just write here this one. PA interception B up to here is given, no? Then write A given B, PA interception B over PB equal PA now, then cross multiply. This equation only possible with independent event, okay? Not with the others, only with independent events. Here PA interception B over PB equal PA. So here only for independent event, okay? Not with the others. Now you go to next page, page number 8. I have given few definitions. In some cases, you have to remember these because sometimes you have to define these events. Okay, this page number 8, those definitions you have to remember. So equally likely event, I told you before, equally likely events are events that have the same probability of occurrence. Okay, equally likely, the occurrence is same. Therefore, equal likely events are events that have the same probability of occurring. Unbiased coin tossing, no? Then head, getting tail, equally likely. Rolling a die, unbiased die. Then getting 1, getting 2, getting 3, getting 4, getting 5, getting 6, equally likely, no? Getting even, getting odd, equally likely. But getting even and multiple of 2 can be different, no? Okay, then exhaustive event, that also very important one. Exhaustive, another definition. A union B, S. See this? A union B, S. Then we say this is exhaustive events. A union B, S. That means by event A and B, fully sample space will be created, no? Then A and B exhaustive. A and B are exhaustive. Then A union B union C equal S. Then again we say A, B and C are exhaustive. That is exhaustive. Okay. Exhaustive events are set of events that cover all possible outcomes. So by those events that cover all possible outcomes, that means that cover sample space, no? Sample space. A set of events is exhaustive if their union equals to the sample space. That is very important definition. Some cases you have to remember, in some years we got that one, we have to apply them directly. Then independent events. So two events are called independent if the occurrence of one does not affect the probability of the other occurring. So A not depend with B, A dash not depend with B, A not depend with B dash, A dash not depend with B dash. If A and B are independent, we say A and B no dependency, A and B dash no dependency, A dash and B dash no dependency, A dash and B dash no dependency. That is we call independent event. Then for independent event, you have to remember this formula. So if AB independent, then if this satisfied, then we say AB independent. In some cases, we have to take that formula, okay? Then you have to remember. Then last one, mutual exclusive, that one I have discussed at the beginning. Mutual exclusive means that cannot happen together. At the same time, that cannot happen, no? Then AB interception null. Then they are mutually exclusive events. Then the probability of A interception B now 0, no? If A interception B null, then probability of A interception B 0, no? that is mutually exclusive. This means no overlap between two events. Then you have to remember those definition. Mutually exclusive mean A interception be null, probability of A interception be 0. If A and B are independent, PA interception B equal PA times PB. Then if A and B are exhaustive, A union B equal S, A union B equal S, then PA union B equal 1. No? PA union B equal 1. Okay, then equally likely events, then all the outcome has same occurrence, same probability of occurrence or same occurrence. Okay. Now we have only one thing to discuss. I'll go a little further. Before that, see this. See this one. I gave you conditional probability now. PA given B equal PA interception B over PB. Okay. Then here by this PA interception B equal PA given B times PB. No? That is just like product formula. Same cross multiply, you can obtain that. Similarly, PB given A equal PA interception B over PA. Then cross multiply PA interception B equal P given A times PA. See here downstairs A we have to multiply with PA. Downstairs B we have to multiply with B. But both are same, no? PA interception B equal PA given B times PB equal PB given A times PA. No? Okay, somewhere you better write that. අලුතින් කොලයක් දැම්මත් කමන්න අතන ස්පේස් තියනවා නම් write down it. Page number 7, if you have space, just put that one. Page number 7 or 8, whatever, just write somewhere. And further we have something, P null given A. So it looks like P null, it is 0. It looks like null, okay? So theorem P null I gave you 0, no? Then P null given A 0. 2 P A dash given B is look like P A dash 1 minus P A given B. If we have P A dash, we write 1 minus P A. Now look like P A dash given B look like same 1 minus P A given B. Okay. Third, P A given C. Here P A interception B given C, P A interception B dash given C. So just forget denominator part. Same theorem we discussed before. P A equal P A interception B plus P A interception B dash. Now C already occurred, then no worries, you can put same theorem. 4 P A union B given C. Write P A given C, P B given C minus P A interception B given C. Given C. Okay, these are previous all theorems. Previous theorems with given condition. Better write them all. These are some theorems with conditional probabilities. Theorems on conditional probability. So no worries, if you write definition, we get that. So no need to remember these theorems, but if you remember that one, that is very, very important. But with the definition, we can obtain all. With previous initial definition, we can take all. Okay, one more thing to discuss. That is somewhat long. That is about partition of sample space, total probability theorem and Bayes theorem. Okay, later we will discuss that one, no worries. Now up to now we done about fundamental definition of probability, historical definition, frequency definition, axiomatic definition and theorems and so on, and conditional probability. No? Then those are very important. So this is very simple question, part A question very simple. Next day we can do all probability, full part we can complete. Okay, then that's enough for today.